For decades, we've been told that black holes are massive, distant monsters lurking at the centers of galaxies. But what if that's only part of the story? What if black holes, small, invisible, and nearly undetectable, are right here in our own solar system, quietly drifting through space, influencing planets, and possibly even explaining one of the greatest mysteries in science: dark matter? Here's the problem. Over 80% of the universe's mass is missing, or at least missing in the sense that we can't see it. Scientists call it dark matter, and for years, they believed it was made of exotic particles. But what if they've been looking in the wrong place all along? Some researchers believe the answer isn't hidden in physics we don't yet understand, but in black holes that formed in the first moments after the Big Bang, primordial black holes, PBHs. And if that's true, these objects could be all around us, even within our own cosmic neighborhood. But how do we find something that doesn't emit light, doesn't collide with anything, and might be smaller than an asteroid? Scientists are turning to a new kind of telescope, one that doesn't rely on light, but on gravitational footprints. By analyzing the precise motion of planets like Mars, researchers believe they might have already detected the influence of a PBH, without even realizing it. This discovery wouldn't just change how we understand black holes. It could redefine our entire understanding of the universe, galaxies, and even gravity itself. So, how many black holes are really hiding in our solar system? And what would it mean if we found one? The answer might be closer than anyone ever imagined. Do you know what is dark matter mystery? Over 80% of the universe's mass is missing, at least missing in the sense that it can't be seen, touched, or directly measured. Scientists call this elusive substance dark matter, and despite decades of research, it remains one of the greatest mysteries in modern physics. Its existence is undeniable. Without it, galaxies wouldn't hold together, and the universe as we know it would collapse under its own contradictions. Yet, the challenge is that dark matter refuses to interact with light, making it completely invisible to traditional observational methods. So, how do scientists even know it's there? The key lies in gravitational effects. Galaxies spin at speeds that should tear them apart, yet they remain intact. The only logical explanation is that an unseen mass, far greater than all visible stars and planets combined, is holding them together. Think of it like wind. You can't see it, but you can observe its effects on leaves and waves. Dark matter behaves similarly, bending light from distant galaxies and influencing cosmic structures on an enormous scale. The hunt for dark matter has led scientists to some mind-bending theories. Initially, researchers thought it might be ordinary but dim cosmic objects, like rogue planets or black holes. However, careful analysis ruled those out as primary candidates. Instead, the focus shifted toward unknown subatomic particles. Unlike anything found on Earth, these particles, if they exist, could redefine our understanding of physics, bridging gaps between Einstein's theories and the unexplained forces shaping the cosmos. Understanding dark matter isn't just an academic exercise. It's the missing piece in the puzzle of the universe's evolution. Without it, galaxies wouldn't have formed as they did, and the large-scale structure of the cosmos would look completely different. Yet, despite its fundamental role, dark matter remains beyond reach, leaving scientists chasing shadows with increasingly sophisticated experiments. And if dark matter isn't made of exotic particles, what else could it be? Some researchers believe the answer lies in something even more mind-blowing: objects that formed in the first moments after the Big Bang, hiding in the depths of space, influencing everything while remaining unseen. But what are the early theories on dark matter? Before scientists realized that dark matter might be something entirely new, they started with a simpler question: could it just be ordinary matter that we can't see? The first theory suggested that the missing mass of the universe might be hiding in objects that don't emit light, things like dead stars, rogue planets, or black holes. If these objects were floating through space unnoticed, they could explain why galaxies seem to have more mass than what was visible. One of the most popular early ideas involved neutron stars and brown dwarfs, objects too faint to detect with regular telescopes. Neutron stars are the collapsed cores of massive stars, incredibly dense but no longer shining like their former selves. Brown dwarfs, on the other hand, are failed stars that never gathered enough mass to ignite nuclear fusion. Both seemed like reasonable candidates at first, but detailed surveys showed they simply weren't abundant enough to account for the enormous gravitational pull holding galaxies together. Another idea focused on black holes, those mysterious gravitational traps that even light can't escape. Could a vast network of invisible black holes be shaping the cosmos? It was an intriguing thought, but the math didn't add up. While black holes do contribute to the universe's mass, they are far too rare to make up the missing 80%. Plus, if black holes were responsible, we'd expect to see more gravitational lensing, a warping of light caused by their intense gravity, than what's been observed. By the late 20th century, the scientific community had largely moved past these early theories. The universe's missing mass wasn't just hidden stars or rogue black holes. It had to be something else. Something much stranger, beyond anything found in everyday physics. That realization forced scientists to look beyond conventional matter and rethink their entire approach. If dark matter wasn't made of normal matter, then what was it? That question opened the door to a radical shift in thinking, one that would take researchers deep into the world of subatomic physics, where new kinds of particles might be shaping the very structure of the universe itself. And speaking of particle-based theories, one scientist realized that dark matter couldn't be made of ordinary objects like stars or black holes. They turned to the subatomic world. Maybe, instead of missing planets or invisible black holes, dark matter was something entirely different, an exotic type of particle, undetectable by traditional means. This idea led to some of the most fascinating and mind-bending theories in modern physics. One of the earliest candidates was a neutrino, a ghostly particle that barely interacts with anything. Neutrinos pass through planets, stars, and even your own body by the trillions every second without leaving a trace. Scientists thought that if neutrinos had a bit more mass, they could explain dark matter. But there was a problem. Neutrinos move too fast. Instead of helping galaxies stay together, they would have dispersed them like mist in the wind. That meant neutrinos, while fascinating, weren't the answer. Another major candidate was the axion, a theoretical particle that, if real, could help solve multiple cosmic mysteries at once. Unlike neutrinos, axions would be much lighter and more stable, possibly forming invisible fields stretching across entire galaxies. Scientists have designed intricate experiments using supercooled chambers and powerful magnets to try and detect them. So far, nothing, but the search continues, with each new test bringing them closer to a breakthrough. Then came the idea of WIMPs, weakly interacting massive particles. These hypothetical particles would interact only through gravity and the weak nuclear force, making them nearly impossible to detect. If WIMPs exist, they should occasionally collide with ordinary atoms in a way that could be measured. Researchers have built massive underground detectors, shielded from cosmic radiation, hoping to catch a rare WIMP interaction. The results? Still inconclusive. Despite decades of searching, no experiment has confirmed the existence of dark matter particles. But that hasn't stopped scientists. If WIMPs and axions aren't the answer, could the missing mass of the universe be something even stranger? Perhaps black holes formed in the earliest moments after the Big Bang? Some researchers believe the key to unlocking the dark matter mystery isn't found in particles at all, but in the ancient past of the cosmos itself.
Hey, I need your help to be saved from falling into space forever. All you have to do is like the video and subscribe to the channel. Thanks.
But what are the primordial black hole hypothesis? If dark matter isn't made of exotic particles, could it be something far older? Something forged in the first moments after the Big Bang? Some scientists believe the answer might lie in primordial black holes, PBHs, hypothetical objects that formed when the universe was just a fraction of a second old. Unlike the supermassive black holes found at the centers of galaxies, PBHs would be much smaller, some as tiny as an asteroid. yet still possessing immense gravitational pull. The idea is fascinating because PBHs wouldn't require new physics. They'd be made of ordinary matter, but created under extreme conditions we no longer see in the modern universe. If these ancient black holes exist in vast numbers, they could account for the missing mass that holds galaxies together. But there's a catch. No one has ever found direct evidence that PBHs exist. Unlike other black holes, which are detected through their interactions with nearby matter, these would be almost completely undetectable, making them a perfect dark matter candidate. One of the strongest arguments for PBHs comes from the cosmic microwave background, CMB, the faint glow left over from the Big Bang. If PBHs were abundant, their gravitational influence would have subtly altered this ancient radiation. Scientists have examined CMB data for hints of PBHs, but haven't yet found a conclusive signal. That said, the asteroid mass range of PBHs remains a strong possibility, meaning the hunt is far from over. Another challenge is that black holes, even small ones, would occasionally collide with stars or planets. If PBHs are out there, why haven't we seen the telltale signs? Fluctuations in starlight, unexpected gravitational lensing, or strange disruptions in planetary orbits. Some astronomers believe we may have already observed these effects without realizing it, and that a closer look at existing astronomical data could reveal PBHs hiding in plain sight. If primordial black holes truly exist, the implications would be profound. Not only would they solve the mystery of dark matter, but they'd also offer a glimpse into the earliest moments of the universe, where physics operated under extreme conditions unlike anything we see today. But how do you prove the existence of something that barely interacts with anything? Scientists have a bold idea: using the planets in our own solar system as PBH detectors. Using the solar system as a PBH detector. If primordial black holes, PBHs, are out there, they're not just lurking in distant galaxies. They could be passing right through our own solar system without us even noticing. Since PBHs don't emit light, the key to finding them isn't looking at the sky, but tracking their gravitational effects. And what better way to do that than by using the planets themselves as cosmic motion sensors? The idea is simple but brilliant. Planets follow incredibly precise orbits, governed by Newtonian physics and Einstein's relativity. If a PBH were to drift through our solar system, even without colliding with anything, its gravitational pull would cause tiny but measurable shifts in planetary motion. These deviations, though nearly imperceptible, could reveal the presence of an unseen cosmic object. Think of it like a fingerprint left behind in space-time. To test this theory, scientists have started looking at long-term orbital tracking data. Space agencies like NASA have been monitoring planets like Mars for decades, measuring their positions with extreme accuracy. If there's an unexplained anomaly, something that can't be attributed to known celestial bodies, then it could be a sign of a passing PBH. Even a subtle change in a planet's velocity could hold the key to proving their existence. The beauty of this approach is that it doesn't require new telescopes or expensive equipment, just a careful re-examination of existing data. Some researchers believe that past measurements, dismissed as observational errors, might actually be evidence of dark matter PBHs in action. If they're right, it could revolutionize our understanding of dark matter without the need for exotic new physics. Of course, before jumping to conclusions, scientists need a way to separate real PBH signals from other gravitational influences. This is where advanced simulations and computational models come into play. If there's a way to confirm that a planetary anomaly wasn't caused by an asteroid or an undiscovered moon, but by something much stranger, then we might be closer than ever to solving the dark matter puzzle. Gravitational microlensing constraints. If primordial black holes, PBHs, are real, they should occasionally pass in front of distant stars, bending their light in a predictable way, a phenomenon known as gravitational microlensing. This effect, first predicted by Einstein, happens when a massive object warps the fabric of space-time, temporarily magnifying a background star as it moves across our line of sight. Scientists have used this method to search for PBHs, and the results have ruled out many possible mass ranges, but not all. One of the most extensive microlensing studies comes from the OGILI optical gravitational lensing experiment, which monitored millions of stars to detect even the slightest changes in brightness. If PBHs were common, their gravitational influence should have created multiple microlensing events. However, after years of observations, the data showed that PBHs within a certain mass range were highly unlikely to exist. But here's the catch. While OGILI eliminated many mass ranges, it left a small loophole. The asteroid mass range between 10 superscript 1g and 10 superscript 2 superscript 3g remains a viable candidate for PBHs as dark matter. That means, if these tiny black holes exist, they could still be the missing mass holding galaxies together, but they're too small to produce frequent microlensing signals. The challenge now is developing new ways to detect them. Some scientists believe that upcoming surveys, like those from the Vera C. Rubin Observatory, could help settle the debate once and for all. By scanning the sky with unprecedented sensitivity, these future telescopes could catch rare, fleeting microlensing events that previous studies missed. If such signals are found, they could be the long-awaited smoking gun for PBHs. Still, microlensing alone won't be enough. We need another way to cross-check these findings. That's where planetary motion comes back into play. If a PBH is small enough to avoid detection through microlensing, could it still leave a gravitational footprint in our solar system? Some researchers think so, and they're turning to Mars' orbit for clues. If primordial black holes exist, they might not be floating in distant galaxies. They could be passing through our own solar system. The problem is, they'd be nearly impossible to see. So, how do scientists look for something that doesn't emit light? The answer lies in the precise movement of planets, particularly Mars. Mars is one of the most well-tracked planets in our solar system. Space agencies like NASA and ESA have been monitoring its position for decades using satellites, landers, and orbital data. If a PBH were to drift close enough, even for a brief moment, its gravitational pull would cause a tiny but detectable shift in Mars' trajectory. It wouldn't send the planet flying out of orbit, of course, but even a microscopic deviation could signal the presence of an unseen object. To put this in perspective, tracking Mars' position has reached such a high level of accuracy that even a shift of a few meters over millions of kilometers could be noticed. That's how sensitive modern astronomical tools have become. Scientists are now combing through years of Martian orbital data, looking for unexplained anomalies, subtle changes that can't be accounted for by known planets, asteroids, or gravitational effects. The idea is simple but revolutionary. If PBHs are acting as dark matter, they should be everywhere, including in our own backyard. Even a rare close encounter with Mars or another planet could reveal them. Some researchers even speculate that past anomalies, previously dismissed as observational errors, might have actually been PBH flybys all along. But confirming this hypothesis requires more than just tracking one planet. Scientists are now expanding their search, analyzing decades of data not just from Mars, but also from other planets and moons. And with new computational models coming into play, they may soon be able to filter out the noise and identify real PBH signals. The next step? Digging into 2 decades of data to see if anything unusual stands out. For over 2 decades, space agencies have been collecting incredibly detailed data on the motion of Mars, tracking its orbit with precision that was once unimaginable. Now, scientists are turning to this data with a new goal, searching for unexplained gravitational anomalies that could point to primordial black holes passing through the solar system. If even a single unexplained deviation is found, it could rewrite our understanding of dark matter and the structure of the universe. The challenge, however, is separating true PBH signals from ordinary gravitational influences. The solar system is a dynamic place, with constant interactions between planets, asteroids, and even the subtle gravitational pull of distant celestial bodies. To find a possible PBH, Researchers need to analyze decades of orbital data, running sophisticated simulations to rule out known influences. The slightest miscalculation could lead to false positives, making this an enormous computational challenge. One of the key tools in this search is deep space network tracking, which provides millimeter-level precision in measuring planetary positions. These signals bounce off spacecraft orbiting Mars and return to Earth, creating an extraordinarily accurate dataset of the planet's motion. If a PBH passed through the solar system unnoticed in the past, its gravitational fingerprint might already be hidden within this treasure trove of information, waiting to be discovered. Beyond Mars, other planetary tracking programs are being considered. Data from Jupiter and Saturn could provide additional evidence, as their massive gravitational fields make them ideal for detecting even the slightest perturbations. Scientists are also exploring long-term lunar laser ranging, bouncing lasers off reflectors left by Apollo missions, to check if the moon's orbit has experienced any unexplained influences. If an anomaly is found, the real work begins, determining whether the culprit is an asteroid, an undiscovered object, or something far more exotic, like a PBH. And if that's the case, it raises a fascinating question. Could we pinpoint one of these hidden black holes and track its motion in real time? That's where future observations will play a crucial role. Finding a gravitational anomaly in planetary motion is just the beginning. If an unusual shift is detected in Mars' orbit or in the motion of other celestial bodies, the next step is confirming whether the culprit is a known object, like an asteroid, or something far more elusive, like a primordial black hole PBH. This is where future astronomical observations will play a decisive role. Scientists will need to track these anomalies over time, using next-generation space observatories to rule out conventional explanations. If an asteroid is responsible, it should eventually become visible as it moves closer to Earth or reflects sunlight. A PBH, however, would remain completely dark, only revealing itself through continued gravitational interactions. This means that over the next few years, astronomers will have to monitor planetary orbits with even greater precision, looking for patterns that can't be explained by ordinary physics. New telescopes, like the Vera C. Rubin Observatory, will scan the sky in unprecedented detail, capturing subtle changes in starlight and planetary positions. Meanwhile, missions like the ESA's Gaia are already tracking millions of stars with millisecond precision, enough to detect even the slightest distortions caused by hidden masses in our cosmic neighborhood. These tools could provide indirect evidence of PBHs by observing how they disturb surrounding space. Another approach involves deep space gravitational wave detectors, which could eventually pick up signals from PBHs interacting with each other. If two primordial black holes were to collide, they'd release a burst of gravitational waves that could be detected by instruments like LIGO, Virgo, and future space-based detectors like LISA. While this wouldn't confirm that PBHs make up dark matter, it would prove that these objects exist, opening a new chapter in our understanding of the universe. If astronomers do detect an invisible gravitational force affecting planetary orbits, it could mean that dark matter isn't made of exotic particles at all, but of ancient black holes scattered across the cosmos. But to separate real signals from background noise, enormous computational resources will be required. Scientists will have to simulate millions of possible scenarios to distinguish a true PBH interaction from ordinary gravitational effects. Detecting a primordial black hole isn't just about looking through a telescope. It's about crunching an immense amount of data. The slightest gravitational anomaly in planetary motion could be the key to proving PBHs exist, but separating a real signal from background noise is a monumental challenge. That's why scientists are turning to supercomputers and artificial intelligence to simulate every possible scenario and extract meaningful patterns. Every celestial body in the solar system influences the motion of others, creating a complex web of gravitational interactions. To pinpoint a PBH's signature, researchers need to run massive orbital simulations, accounting for every known object, from planets and moons to passing asteroids. Even a minor miscalculation could lead to false positives, So these simulations require millions of iterations to distinguish real effects from natural variations. One of the biggest hurdles is that planetary orbits are already affected by multiple forces, including solar radiation pressure, gravitational tugs from passing comets, and even tiny effects like the Yarkovsky effect, a minuscule force caused by heat emitted from a rotating asteroid. Eliminating these factors from the data is no small task, which is why some of the world's most powerful supercomputers are being used to process and refine orbital tracking models. Artificial intelligence is also playing a crucial role. Machine learning algorithms can scan through decades of observational data, identifying subtle deviations that would take human researchers years to detect manually. By feeding AI models with simulated PBH encounters, scientists are training systems to recognize the difference between ordinary gravitational effects and something truly anomalous. If a real PBH signature emerges from this analysis, it would mark a historic breakthrough, not just for dark matter research, but for our entire understanding of the universe, galaxies, and the fundamental forces that shape reality. The next step? Using this knowledge to predict when and where a PBH might pass again, opening the door to direct observations and deeper cosmic exploration. If primordial black holes really exist within our solar system, we might be standing on the edge of one of the biggest discoveries in the history of science. Think about it: hidden black holes, influencing planets, and possibly solving the dark matter mystery. It's the kind of revelation that could force us to rewrite physics, reimagine the structure of the universe, and finally understand what's really shaping the galaxies around us. But here's the question: how close are we to actually finding one? Could a PBH have already passed near Earth, altering the orbits of planets without us realizing? If so, what else could be hiding in the dark corners of our cosmic neighborhood? The answers are still out there, waiting to be uncovered, and with new telescopes and AI-driven data analysis, we might be closer than ever. Now, I want to hear from you. Do you think black holes are lurking within our solar system? Could they be the key to dark matter? Or is there something even stranger going on? Drop a comment, and let's explore this mystery together. And if you want to dive even deeper into the secrets of the cosmos, don't stop here. Watch our previous video, What Really Happened Right After the Big Bang? You won't believe how much of the universe's history is still unknown. Make sure to subscribe and turn on notifications, because we're just getting started uncovering the greatest mysteries of the universe.